Good morning. Welcome to the IAPD web seminar, Demystifying Engineering Plastics. My name is Wendy Shantz, and I'm IAPD's Marketing and Education Manager. IAPD is your source for trusted plastics information. You can visit iapd.org for more information. Today's web seminar is presented by Keith Hectel, Director of Business Development for Curbell Plastics, Inc., based in Orchard Park, New York. Keith has a doctorate in Business Administration degree, a Master of Science degree in Industrial Technology, and over 20 years of plastics industry experience. Much of his work involves helping companies identify plastic materials that can be used to replace metal components in order to achieve quality improvements and cost savings. Keith is a recognized speaker on plastics materials and plastic part design. He has conducted numerous presentations for engineers, designers, and fabricators in both industrial and academic settings. We are honored to have him as our presenter today. Before we get started, please note that Keith will answer your questions after the web seminar. You may use the Questions tab on your webinar tool to send questions, which will be read aloud at the conclusion of the seminar. If you would like a copy of today's presentation, please complete the evaluation that will be emailed to you after the seminar. A link to download a PDF copy of the web seminar is at the end of the evaluation. And now, without further ado, here's Keith on what is demystifying engineering plastics.
Okay, thank you, Wendy. And first of all, thanks to Wendy and IAPD for inviting me to speak today. This is my first webinar, so if I'm a little bit slow on the technology, please bear with me. Is my audio coming through okay, Wendy?
You sound good, Keith. Thanks.
Okay. First of all, I'd like to thank the participants who are joining us for the webinar. And I recognize that in today's environment, everybody is extremely busy at work, and it's an investment of your time to participate in a webinar. So I thank you for taking the time. And the purpose of the webinar today is to talk about engineering plastics, and specifically to develop a methodology for selecting the right engineering plastic for an application. When engineers and fabricators and plastic sales professionals are confronted with the task of selecting an engineering plastic for an application, it's often kind of daunting. There are dozens and, in fact, hundreds of plastics out there, and it's hard to know where to start. Where a lot of people start is by reviewing the commercial literature on plastics that they're familiar with or plastics that they've heard of. Sometimes the qualitative descriptions that you read in the commercial literature can be a little bit confusing. They don't always provide sufficient detail to help you select the plastic material. So we have an example here of a description of a common commercially available plastic, ABS. And it's described as a strong, tough engineering plastic with excellent machining characteristics and outstanding performance in demanding environments. We also have a commercial description of acetal, described as a strong, tough engineering plastic with excellent machining characteristics and outstanding performance in demanding environments. And clearly, when you look at that qualitative description, it applies to both plastics, and it makes it very hard to choose between the two plastics for an application. So here's what we're going to look at today. Number one, we're going to look at amorphous and semi-crystalline thermoplastics. We're going to discuss the characteristics of amorphous plastics and the characteristics of semi-crystalline plastics to start to develop some ideas about when one would perhaps be more appropriate for an application and where perhaps the other one would be more appropriate for an application. Then we're going to shift gears a little bit and look at the properties of materials for people who are unfamiliar with them. And when you look at a property sheet for plastic materials, you'll see that there are 15 or 20 properties listed for a plastic. And it can be a little bit daunting as far as where do I start and how do I start comparing plastics based on their properties. Well, I have found these 4 properties to be very helpful when comparing plastic materials, and they don't give you all the information about a plastic, but they give you a nice feel for what that plastic is all about. Once we've discussed amorphous and semi-crystalline plastics, and talked about these 4 properties of materials, we're going to overlay those 2 ideas and develop a methodology for selecting either an amorphous or semi-crystalline plastic based on their characteristics and based on those 4 properties. To summarize all that, when selecting a thermoplastic material, I like to consider the following 2 questions. Number 1, do the application requirements more closely fit an amorphous or semi-crystalline thermoplastic? And number 2, what material properties are relevant for the application? So let's start off with amorphous and semi-crystalline plastics. And when you look at the molecular structure of an amorphous thermoplastic, it looks kind of like a plate of cooked spaghetti. It has a very disorganized molecular structure. And if you look at the molecular structure of a semi-crystalline thermoplastic, it will have regions of crystallinity throughout the molecular structure. Now, for the chemists in the group, I'll qualify that by saying it's a little bit of an oversimplification. There's actually a range of crystallinity that you can achieve in plastics by controlling things like additives and chemistry and cooling rates. But that being said, it's very helpful to think of plastic materials as either amorphous or semi-crystalline thermoplastics. When I think about the plastic failures that I've seen throughout my career, a lot of times the source of the failure is when someone used an amorphous plastic where perhaps a semi-crystalline would have been more appropriate, or they used a semi-crystalline where perhaps an amorphous would have been more appropriate. So I think, in addition to material selection, this is a helpful way to start diagnosing failures and problems that people have with plastic materials. Additionally, there's another useful way to think about plastic materials. You can arbitrarily divide them into 3 groups. Commodity plastics, which are kind of inexpensive, low-temperature plastics that don't exhibit high-performance characteristics. So they're common plastics that you would see in everyday applications. Moving up the scale a little bit, you have engineering plastics, which tend to be higher temperature, higher cost, higher performance materials. And finally, at the top of the scale, you have high performance materials that tend to be able to withstand high service temperatures. They tend to have high performance characteristics, and they tend to be quite expensive. So if I overlay these 2 ideas, dividing thermoplastics into amorphous and semi-crystalline thermoplastics, and further dividing them into commodity plastics, engineering plastics, and high-performance materials, I yield a fairly complicated-looking diagram. Now, you'll see this triangle in many different forms throughout plastics literature, and IAPD does a nice job of summarizing the same information on the IAPD rectangle. And what you see here is all the amorphous plastics, or many commercially available amorphous plastics, are on the left in pink. On the right in blue, you'll see semi-crystalline plastics, and at the top of the triangle, you'll see these imide materials, and they won't really be part of our discussion today. Perhaps if IAPD has me back at some future point, we can talk about those. But the important thing to remember for today is the amorphous plastics are in pink on the left, and the semi-crystalline plastics are in blue on the right. I'm going to try my highlighter here and say we've got this divided now into 6 different families of plastics. I have the commodity plastics at the bottom, and these are the amorphous commodities. Moving up the scale, I have amorphous engineering plastics. And moving further up the scale in cost and temperature and performance, I have amorphous high-performance materials. Jumping over to the right side of the chart, I've got semi-crystalline commodity plastics. followed by semi-crystalline engineering plastics, and finally, semi-crystalline high-performance materials. For the purpose of today's discussion, we're not going to talk too much about the imide materials at the top of the triangle. Now, whether you're talking about a commodity plastic, an engineering plastic, or a high-performance material, all amorphous plastics tend to have certain things in common. And all semi-crystalline plastics tend to have certain things in common. And that's going to be part of our discussion today, is to really focus on the characteristics of amorphous plastics and semi-crystalline plastics. So before moving on, I'd like to say two things. Number one, I recognize that we have a lot of different participants on the conference call, and they come from different industries and different market segments. So rather than drawing examples from complex market segments like medical or semiconductor or aerospace, I'm going to draw my examples from things that you see in your everyday life. And that's not intended to simplify the presentation, but it gives everyone a conventional frame of reference. Number two, at this point, I'm going to ask you to take out a piece of paper and a pen. And I'm going to ask you to take some brief notes, which will be relevant as we get further into the discussion. So on to the next slide. What we've done here is zoomed in on just the bottom portion of that triangle so we can really look at these characteristics of amorphous thermoplastics and semi-crystalline thermoplastics. The first thing you'll notice about amorphous thermoplastics is they soften over a broad temperature range. So you can take a sheet of an amorphous plastic like polystyrene or ABS, and you can heat it up, and it will achieve a rubbery consistency like soft pizza dough. And I remember as a kid growing up on Long Island watching the pizza guy throw the dough up in the air and catch it and stretch it with his hands. That's the perfect consistency for people who do thermoforming. They want to be able to heat up that plastic sheet and mold it over a mold to achieve a certain part geometry. That's very easy to do with amorphous plastics because they have that broad temperature at which they will be soft and behave like pizza dough. That makes them very easy to thermoform. On the other hand, if you look at semi-crystalline plastics, they tend to have a sharp melting point. They go from being rigid to being very soft and melted, and they're very difficult to thermoform. As one very eloquent thermoformer told me, they got no hot guts. They don't have that nice rubbery phase over a broad temperature range. It's over a much narrower temperature range. I'm not saying you can't thermoform semi-crystalline plastics. You certainly can. People thermoform polyethylene truck bed liners every day. What I am saying is it's more difficult than thermoforming amorphous plastics. You need to have special molds, and you have a much narrower processing window. On to the next characteristic, which is transparency. Amorphous plastics tend to be transparent. Not all of them, but most of them. And I can remember 2 summers ago going out to SeaWorld and looking at the tank for Shamu the whale. And it was 6-inch thick acrylic. And I was looking at Shamu, and he was looking at me, and I didn't realize that Shamu likes to splash visitors with seawater with his tail. So I was drenched from head to foot while looking at this transparent amorphous plastic. And what's great about amorphous plastics, they could make that very thick tank, and it was still optically clear. Now, semi-crystalline plastics tend to be opaque. So if I had 6-inch thick acetal or 6-inch thick polyethylene, it certainly would not have been clear. Now, I'm not saying semi-crystalline plastics can't be transparent. In very thin sections and modified with certain additives, you can make things like optically clear polypropylene film to perhaps wrap up flowers and give them to somebody. What I am saying is it's much more difficult to make semi-crystalline thermoplastics transparent. because they tend to be opaque. Moving down the list, amorphous plastics tend to have poor chemical resistance. Semi-crystalline plastics tend to have good chemical resistance. And at this point, it's probably a good time to throw in a little bit of philosophy along with plastics. A property is neither good nor bad, it simply is. And by that I mean having good chemical resistance or poor chemical resistance can be both a blessing and a curse. Certainly if you're handling chemicals, it can cause difficulty to have an amorphous plastic with poor chemical resistance. So to give you an example, it is springtime here in Buffalo, and the snow melted last week. So now it's really warm and tropical here. And I took out my lawnmower that I had put away last fall when I broke out the snowblower, and it had a little bit of extra gasoline in the gas tank. And I poured that into the styrofoam cup that I drank my coffee out of that morning. And unfortunately, styrofoam is an amorphous plastic with poor chemical resistance. It immediately dissolved the cup, and the gasoline made a huge mess on the floor of my garage, which I had to make my son clean up. On the other hand, when I looked at the gasoline container, that red container that everybody has in their garage, that was made out of a semi-crystalline plastic, polyethylene, which has terrific chemical resistance. You can store that gasoline in there for years and never have a problem. Now, I said that having chemical resistance was both a blessing and a curse. The next characteristic of amorphous plastics is that they tend to bond well when you're using adhesives or solvents, specifically because they have poor chemical resistance. Those of you who are like me and made plastic models when you were a kid can remember taking out that tube of polystyrene cement and dabbing it on the model parts and then joining them together, and they would instantly bond and give off a lot of wonderful fumes while you were doing it. And after your model was assembled, it was very easy to paint that model with spray paint or a paintbrush. And the reason that that model was so easy to bond with glue and so easy to paint was because it was made out of polystyrene, which is an amorphous plastic. And in this case, having poor chemical resistance was an advantage because it allowed that polystyrene cement to soften the polystyrene and stick the parts together real well. And it allowed that paint to stick really well to the surface. On the other hand, semi-crystalline plastics, because they have good chemical resistance, are very difficult to bond using adhesives or solvents, and they're very difficult to paint. So if you don't believe me, go home today and grab 2 milk jugs and try and glue them together, and it's a miserable experience. Now, we do have a gentleman at our company who specializes in adhesives, and he is a chemist, and I know that Rick can glue together 2 wax candles if he decides to. So it's not impossible to bond semi-crystalline plastics, but it is a lot more difficult than bonding amorphous plastics because they have lousy chemical resistance. Moving on, amorphous plastics tend to be more prone to stress cracking and fatigue resistance. So if you think about the things that can cause fatigue, they could be things like a cyclic thermal stress. You raise and lower and raise and lower and raise and lower the temperature. Or perhaps a repeated mechanical stress. You load and unload or load and unload a specimen. Or you take plastic and you bend it back and forth till it breaks. To give you an example in your everyday life, when you go home today, look at your remote control for your TV set. And I remember watching my kids take that battery compartment on the back of the remote control, and while they were watching cartoons, they would open it and close it and open it and close it and open it and close it. And eventually the little clip that was made out of an amorphous plastic that holds the remote control together would fail. And now I have 2 choices, either have the batteries fall out Or take a big piece of duct tape and wrap it around your remote control. And when you go home today, I would invite you to look at your remote control and see how many of them are wrapped in tape because the battery compartment cover failed due to a fatigue failure because it was an amorphous plastic. On the other hand, semi-crystalline plastics tend to have good fatigue resistance. When you think about things like a polypropylene tackle box, and you can bend it back and forth and open it and close it and open it and close it, and that living hinge on the tackle box stays in place because it's a semi-crystalline plastic with terrific fatigue resistance. Finally, when I think about amorphous plastics, they tend to be for structural applications only. I can make a table. I can make a shelf. I can make a holder, something that simply has to take a load. Where semi-crystalline plastics can not only be used for structural applications, but many of them are good for bearing and wear applications, where things are sliding, things are rubbing, like gears and bearings and bushings. So when you think about these two groups, and I want to characterize them, to summarize, I could say amorphous plastics have this great thermoformability. They soften over a broad temperature range. They tend to be transparent. They have poor chemical resistance, not to every chemical, but to many chemicals, which allows them to bond well using adhesives or solvents. They tend to be more prone to distress cracking and fatigue cracking, and they're for structural applications only. To summarize semi-crystalline plastics, they tend to have a sharp melting point, which makes it more difficult to thermoform them. They tend to be opaque. They tend to have good chemical resistance, again, not to every chemical, but to many chemicals, which makes them hard to bond using adhesives or solvents. They tend to be resistant to stress cracking and fatigue failures, and many of them, if not all of them, are good for bearing and wear applications. So, let's look at some examples from our everyday lives. And I'm going to start off with a thermoformed polystyrene coffee cup lid. And many of us start our morning with a cup of coffee with one of these lids pressed over the top. These lids it is essential that these lids be easy to thermoform. And so they've chosen an amorphous plastic because of its easy thermoformability. And polystyrene is widely used because it's easy to thermoform and it's inexpensive and it doesn't ruin the taste of your coffee. Moving on to the next example is an automobile tail light. And for a tail light to be functional, it needs to have this wonderful optical clarity. And in many cases, they'll use acrylic for these tail lights because they have optical clarity, and acrylic is an amorphous plastic, and amorphous plastics, of course, tend to be transparent. It would certainly cause a lot of accidents if you had a Delrin tail light because you wouldn't have the transparency since it's a semi-crystalline plastic. Moving on to the next example, we have some plastic plumbing pipe. And in this case, it's CPVC. And it's great to have an amorphous plastic for plastic plumbing pipe because it makes it so easy to bond using solvents and adhesives. And for those of you who've assembled plumbing pipe, you know you can get that applicator of PVC cement, and it gives off wonderful fumes from the solvents, and you dab a little circle around the inside of the pipe, and when you jam those two pieces together, you better get it right because they're never coming apart because they're an amorphous plastic, and that poor chemical resistance allows you to bond that pipe. In contrast, it's very difficult to do that with semi-crystalline plastics like high-density polyethylene pipe, which you have to weld via thermoplastic welding. Now, I'm not saying that plumbing pipe can't resist any chemicals. It'll certainly resist that orange hair dye that my 12-year-old daughter flushes down the drain. However, for thermoplastic plumbing pipe made from amorphous thermoplastics, I wouldn't want to put things like aggressive solvents down the drain because it's an amorphous plastic chosen for its ability to bond well using solvents and adhesives. Moving on to the next example, which is a point-of-purchase display. And in this case, that display was made out of an amorphous thermoplastic, and they chose that for two reasons. One, you get this beautiful optical clarity. And number two, it was easy to put that display together with solvent adhesives. Finally, I'm looking at an outdoor sign showing "Welcome to Fabulous Las Vegas." And sign makers love amorphous thermoplastics for a number of reasons. One, they need the transparency, especially if you're going to have a backlit sign, you need it to be able to transmit light. Number two, it's easy to paint an amorphous plastic and have the paint stick to it, or to screen print. And number three, it's easy to bond with adhesives or solvents if I have to glue letters to the front of the sign. Finally, many outdoor signs are thermoformed, and amorphous thermoplastics tend to be easy to thermoform. So if you think about the materials used by sign makers, it's materials like acrylic and materials like polycarbonate that are easy to thermoform and transparent, and they are, of course, amorphous thermoplastics. Look at the chemical containers in your life, whether it's holding acetone or holding bleach, or perhaps that gasoline container that we mentioned earlier. These are usually made out of semi-crystalline thermoplastics because you need that chemical resistance. You certainly wouldn't want an aggressive chemical like nail polish remover or bleach packaged in an amorphous plastic because you'd have more likelihood of chemical attack and failure. On a much bigger scale, here are some industrial chemical tanks. The one in the lower left was welded together via thermoplastic welding. The one in the upper right was rotationally molded. In both cases, the designers chose semi-crystalline plastics because of their terrific chemical resistance. And if you think about the materials used in chemical storage tanks, polyethylene, polypropylene, PVDF, they're all semi-crystalline plastics chosen for their chemical resistance. The sheaves for cranes or the pulleys for cranes, they pick semi-crystalline plastics, in this case nylon, because of their terrific wear properties. And if you can imagine that wire rope running over that crane pulley all day long, you need to have those wear properties of a semi-crystalline plastic. So when you think about these examples from your everyday life, you can see that it makes a lot of sense. Designers are very clever about whether they're picking amorphous or semi-crystalline plastics. And intuitively, when you look at the plastics that surround us in our everyday lives, it makes a lot of sense the way they're doing it. But that's only half the story. Oops, I had one more example. A plastic gear, and in this case they chose nylon, which is a semi-crystalline thermoplastic, for its wear resistance and its fatigue resistance as those teeth are repeatedly stressed, and its stress crack resistance. You certainly wouldn't want to make a plastic gear out of materials like acrylic or polystyrene. Now, I would like to shift gears on you, and let's talk about the properties of materials. Because as I mentioned, one slide too early, the amorphous or semi-crystalline side only tells half of the story. It's really important then to look at the properties of materials. So we're going to look at 4 of them: tensile strength, flexural modulus, notched eyes-out impact strength, and heat deflection temperature. I want to start off by saying that 4 properties are not really enough to fully characterize a material, but it's a good place to start to get a feel for what that material is all about. As you read more about plastics and learn more about plastics and get more engaged in the properties of materials, there are another dozen or so properties that will really help you to develop a rich picture of what plastics are all about. So let's start off with this first property, which is tensile strength. And that's the maximum stress you can put on a specimen where you go to pull it apart. So you can imagine grabbing two ends of this specimen and just pulling it apart till one of two things happens. It either permanently stretches, which is called tensile strength at yield, or it snaps right in half, which is called tensile strength at break. And if you think about tensile strength in your everyday life, think about grocery shopping. When you go to the grocery store and the kid behind the cash register takes 3 2-liter bottles of grape soda, puts them in the same flimsy plastic bag, and hands it to you. And when those bottles exceed the tensile strength of the bag, they fall out and crash onto the floor. A very important property of grocery bags. Additionally, think about the people who have to design the chains for chandeliers. And they look at the links of those chains and say, you know what, there's going to be a pulling stress on this chain. What tensile strength material do I need to be functional for this chain? In addition to looking at tensile loads where things are being pulled apart, I really like to look at the tensile strength of the material because it gives you a good general feel for how strong the material is. It's a common test that everyone can relate to. I'll move on to the next property, which is flexural modulus, which is the amount a plastic will bend under load. And another way to say flexural modulus is stiffness. I'd like to give you an example from your everyday life. For those of you who are sitting at a desk, reach around your desk and grab a pencil and grab a pen. And because I work for Curbell Plastics, I stay at very prestigious hotels where they give away free pens with green caps. So if you've got a hotel pen, for those of you who travel for business, grab that one and hold it in your fingers, as I did here, where you can see I have no future as a hand model, and I put a stress on the pencil. I tried bending it with my fingers. Now, for those of you big moosey people, don't break it. Just bend it a little bit. And then pick up the pen and put a stress on the pen and bend that with your fingers. And if you apply the same stress to the pencil and the cheap hotel room pen, you'll see that the pen bends a lot more than the pencil. In engineering terms, I applied the same stress to the pencil, but I had a much higher strain rate to the pen because the pen had lower stiffness or lower flexural modulus. The pencil is made out of wood, which is a much stiffer material or a higher flexural modulus material. Moving on to the next example, which is notched izod impact strength. That is the energy that it takes to break a plastic specimen. And the way that test is done, they take a plastic specimen and they cut a notch in it. And then they smack it with a hammer mounted on a pendulum. And they look at how much energy it takes to break the specimen. And this is a general measurement of the toughness of a material. Let me give you an example from your everyday life. When I was first married 18 years ago, they gave us a set of ceramic cups with tiny little holes in the handle so I could barely get my finger through. And when I felt those ceramic china teacups, they were very strong. In fact, you can stand on one if you're careful. They're very stiff, so if you take them and flex them in your hand, they feel very stiff. But if you take one of those and you hurl it against a brick wall, they'll shatter into a million pieces. And I found out this is an exceptionally bad thing to do with the china cups that you were given for a wedding present, even if it was for the sake of science. On the other hand, let me contrast that with that plastic coffee mug that you have sitting in your car, the one that you wash once a week, whether you need it or not. And that mug is not very strong. In fact, if you stand on it, it will mush. That mug is not very stiff. You can flex it in your hands, but that mug is incredibly tough. And if you throw it against a concrete wall someday in frustration, it will simply bounce, get a little scratch, and it will be suitable for many more years of drinking coffee in your car. I like the mug versus plastic mug example because it relates directly to this issue of IZOD impact strength, the ability of a specimen to take an impact and not break. Finally, let's talk about heat deflection temperature. And this is the temperature at which a plastic material will soften and deflect under load. So the way this test is done, a load is applied to a specimen, and they use two different loads depending on what plastic you're testing, either a 66 psi load or a 264 psi load. And this happens inside a heated test chamber. And you start to turn up the temperature of that chamber while the load is applied. And eventually, that plastic material will bend. And when it does, you record the temperature at which it bent, and you say, aha, the heat deflection temperature for this material at a 264 psi load is 250 degrees Fahrenheit, or whatever it is. Now, I want to throw in a big word of caution about heat deflection temperature. The temperature at which you can successfully use a plastic material has a lot of complexity to it. Many things come into play. Dynamic modulus, as Larry DeSanto from Ensinger discussed. Thermal stability, how long it will take for the plastic to get brittle. Creep characteristics, will the plastic move around over long periods of time? And perhaps if IAPD invites me back for a future webinar, we can talk in rich detail about what makes a plastic suitable for use at elevated temperatures in an application. That being said, heat deflection temperature is a nice place to start. It shows you that temperature at which a plastic will soften under a specified load to a specified degree. To think of an example in your everyday life, you have to go no further than your microwave. When I ask my kids to heat up the leftover spaghetti, they take it out of the fridge, they put it in a plastic container, throw it in the microwave on high for 25 minutes, and then go and watch cartoons. And eventually, under the load of the spaghetti and the sauce, that plastic container will soften to the point where it actually deforms. And different plastics will soften at different temperatures. So now we've talked about 4 properties of material. Tensile strength, the general strength of a plastic as you're pulling it apart. Flexural modulus, how stiff the plastic is. Heat deflection temperature, the temperature at which it will soften. And notched IZOD impact, how tough a plastic is. And even though this didn't fully explore all the properties of material, if I know how strong it is, how stiff it is, how tough it is, and the temperature at which it'll get soft, I start to get a feel for what that plastic will do. What we've got here are several different property comparisons. And for our first example, we picked 3 transparent amorphous thermoplastics. So these are all from the same family. We've got acrylic, PETG, and polycarbonate. And when you're presented with these 3 materials, what can we say about them? Well, they're all amorphous plastics, so they're going to have many of the characteristics of an amorphous plastic, such as transparency and good thermal formability. However, we can go a little bit deeper and say, hey, how do they compare in terms of tensile strength? How strong are they? Flexural modulus, how stiff are they? Notched IZOD impact, how tough? And heat deflection temperature, at what point will they soften? And let's take those one at a time. Let's look at tensile strength. And here I have acrylic, PETG, and polycarbonate, and we've graphed tensile strength on the y-axis. Well, I can start off by saying acrylic is the strongest. Polycarbonate is a little less strong in tension, and PETG is quite a bit less strong. Now, I'm not saying acrylic is better or worse. because properties are neither good nor bad, but I can say that the acrylic is the strongest and the PETG is the least strong. Then I move on to stiffness, flexural modulus. Well, you can see the acrylic is clearly quite a bit stiffer than either PETG or polycarbonate. And if you think about an application in your everyday life, if I were going to make a shelf to hold perfume, I might want to use acrylic because it's quite stiff. On the other hand, if I wanted a material that felt a bit less stiff, I might choose PETG. Now, on to notched eyes-out impact strength. This is the toughness of the material. And you can see acrylic is characterized by fairly low toughness. It's quite brittle. If you don't believe the graph, go to your local mall and look around at all the displays that the kids working at the mall have knocked on the floor. And you see acrylic, while it's beautifully clear and quite strong and quite stiff, is quite brittle. PETG is significantly tougher than acrylic. If I jump from 0.4 to 1.7, it's perhaps 4 times as tough. But wow, look at polycarbonate, which is in fact used for many bullet-resistant applications. And the military uses polycarbonate in their transparent armor because it is incredibly tough and, in fact, when used in the proper design, can stop bullets. And then let's move on to heat deflection temperature, the temperature at which the plastic gets soft. You can see that PETG softens at relatively low temperatures, followed by acrylic, and then here's polycarbonate. So, heat deflection temperature of 270 degrees Fahrenheit, quite a bit higher than either acrylic or PETG. And when you ask the question, why are acrylic and PETG generally considered commodities while polycarbonate is considered an engineering plastic, you only have to look at this very high toughness and very high heat deflection temperature to see why that's considered an engineering plastic and it's seen such wide use in industry. On to our next example. Now in this case, we've done something quite different. We've taken an amorphous plastic, polycarbonate, and we've compared it with a semi-crystalline plastic, nylon. These are going to have quite different characteristics. Polycarbonate, being amorphous, will have beautiful optical clarity and be easy to thermoform. It'll be easy to paint and easy to bond with adhesives. That being said, nylon, being a semi-crystalline plastic, will have better chemical resistance and better bearing and wear properties. And perhaps I'm trying to find a solution to an application problem. I had mistakenly used polycarbonate for a bearing or a gear, and now I want something similar in properties but will have better wear characteristics, and I'm looking at nylon. Well, when I start off with strength, I can see that the nylon is quite a bit stronger than the polycarbonate. When I go over to stiffness, I can see that the nylon is quite a bit stiffer. That being said, when I look at notched eyes-out impact, the nylon doesn't have nearly the impact strength of polycarbonate. It's quite a bit more brittle. When I go over to heat deflection temperature, the polycarbonate will withstand higher temperatures before it softens under load. And if I say, well, which is the better material, polycarbonate or nylon, I have to answer the question in 2 ways. Number one, do I want an amorphous or semi-crystalline plastic in this application? Do I need the transparency and thermoformability of an amorphous, so I might choose polycarbonate? Or do I need the wear resistance and chemical resistance of a nylon? I might choose that semi-crystalline plastic. The second way I have to answer the question is, what are the important properties for the application? Do I need very high strength and stiffness in favor of the nylon, or do I need toughness and high temperature and maybe favor the polycarbonate? So you can see in this example, when you overlay those 2 ideas, the amorphous and semi-crystalline plastics and the properties, it's very helpful in the material selection process. I want to do just one more example for you, and it's this effect of glass fillers. You can take many plastic materials and add glass, whether it's chopped glass or woven glass or long fiber reinforced glass, and you can significantly change the properties. Now, I'm not saying that glass-filled are better or worse materials. They're simply different. So in this case, I've taken polycarbonate and glass-filled polycarbonate and compared them. Number one, I can see a huge jump in tensile strength when I add the glass, from 9,500 psi to 16,000 psi. Number two, I see a huge jump in stiffness. The polycarbonate went from 345,000 psi to more than double at 800,000 for the glass filled. Notched izod impact strength, I have a different story. The polycarbonate with a notched izod of 12 to 16 is quite a bit tougher than the glass filled, which goes down to 2. Now I want to step back here and say that glass filling has kind of an odd effect on plastics. It makes the very tough ones a bit more brittle, and it makes some of the more brittle ones, like polyether imide, tougher. So I tend to see it as kind of a normalizing factor. It brings that izod impact in that 2 range. Finally, when I look at heat deflection temperature, I can see that the glass filler bumped the heat deflection temperature up by about 25 degrees. So if I were to characterize this, I'd say, well, the glass filler is going to make the plastic stronger and stiffer. For polycarbonate, at least, it'll make it more brittle, and it'll make it take a little higher temperature before softening. Additionally, I have to point out that the glass filler is going to ruin the optics of the polycarbonate and make it opaque. So, a few concluding remarks. Number one, amorphous and semi-crystalline plastics have distinct characteristics that will allow them to perform favorably in different applications. There are instances where you could use either, but there are many other instances where you're better off using one or the other. Number two is a basic property comparison. The strength, stiffness, toughness, and heat deflection temperature of a plastic provide important information about the relative performance characteristics of plastic materials. How does nylon compare with polycarbonate? How does Teflon compare with acrylic? And when you overlay those two ideas, you really are a step closer to doing a very solid material selection. I would invite all of you as a next step, if you found this interesting, to develop a richer understanding of plastics, start to look at the other mechanical, thermal, optical, and electrical properties, because then you really start to develop a rich picture of what each plastic material is all about. So at this point, I'd like to open up the webinar to questions.
All right. If anybody has any questions, please use the questions tab on the GoToWebinar toolbar, and you can send them to me. And we'll wait just a couple of seconds and for those to come through. Thank you very much, Keith. That was a very informative presentation.
Oh, I'm glad. Now, Wendy, you promised you would sing during the intermission while people come up with their questions. Is that correct?
Not today. Maybe tomorrow.
Oh, okay. For the next one.
Yes, possibly. All right. During the presentation, I'd also like to note that Keith presented a material selection tool, the triangle, and I'd like to let everybody know that they can download a similar tool, the IAPD Thermoplastics Rectangle, for free from the IAPD website at iapd.org. And we'll just wait a couple of seconds more, and it looks like there aren't any questions. If anybody thinks of anything, please send them to me via email at wschantz@iapd.org, and I can send those on to Keith and get him to answer them for us. Oh, we just had one come in, and it is, why didn't you talk about imidized materials? And I believe you covered that at the very beginning. Did you, Keith?
You know, whoever wrote that question is one of my people. And a colleague of mine, Candace Resch out in California, and I just did an entire hour-and-a-half presentation on imidized materials for the Society of Aerospace Engineers, and that is a fascinating hour-and-a-half. Unfortunately, I guess the short answer is Wendy told me after about an hour I had to shut up because that discussion would take another hour, hour-and-a-half. But they are fascinating materials, and they will do things that other plastic materials will not. And the short version is they have temperature properties. At very elevated temperatures they will perform. At very cold temperatures some of them will perform. They have outstanding bearing and wear properties. In some respects, they have terrific dimensional stability. So we could do an entire program just on those. They're very fascinating materials.
All right, and we've had a couple more come in. The next one is, can you further explain the difference between tensile strength and IZOD impact?
Sure. I think that's a great question because it's hard to separate those when you think about them intuitively. If you think about tensile strength, it's what it takes to pull something apart. So you can imagine a material like a bungee cord or a steel rod and try pulling them apart, and you'll find out they're incredibly strong. Now, in a similar fashion, imagine a glass rod. And if you hold a glass rod in your two hands and you try and pull it apart, I've got this big 1-inch diameter glass rod and I'm pulling on the two ends, and it has incredibly high tensile strength. There's no way I'm pulling that glass rod apart. On the other hand, if I take that glass rod and I smack it on the side of my desk, it'll shatter into 1,000,000 sharp pieces because it has low IZOD impact strength. So when I think about tensile strength, it's the ability of a material to resist being pulled apart, and think about pulling it apart with your hands in the same way that you'd stretch and pull on a bungee cord. When I think about notched IZOD impact strength, it's the ability of the material to take a shot, to be hit with a baseball bat, to have a brick thrown at it, or to smack it on the edge of your desk.
All right, thank you. And it looks like we have one more. How come when you add glass to clear material, the material is no longer clear?
That's a great question. When you look at any given transparent material, each of them has a unique index of refraction. They'll all bend light a little bit differently. And when you mix materials that have two different indices of refraction, the light will scatter. Now, arguably, if you had a glass fiber and a plastic resin with the identical index of refraction, they both bent light in exactly the same way, you could have a glass-filled material that was still optically clear. But because most plastic materials have a different index of refraction than glass, you're going to lose the transparency as the light scatters at the interface between the glass reinforcement and the thermoplastic matrix.
All right, and another question. You talked about notched IZOD, but what about the notch? No ED.
That's a great question. I think it pertains to why the notch and when do they not use the notch. And the best example I can give is with potato chip bags. And when you think about fighting your way into a potato chip bag, especially after the first six-pack, it can be a miserable experience. And what each of us does intuitively is reach down with your teeth and put a little nick in that potato chip bag to create a stress concentration to start propagating that tear. If you look at many of the things around your office, you'll see that there are sharp corners, whether it's your telephone or your stapler or your computer screen, there are corners. And because engineers want to predict how plastic materials will perform when dropped or impacted, they'll test a material with a sharp corner that has a notch cut into it. Now, in all fairness, there's another way to test materials, which is an unnotched IZOD impact, when you simply smack them with the hammer without notching them. But the notch creates a stress concentration to start propagating that crack, and that more closely simulates real-life applications.
All right, and we've had a few more. I had a customer ask for a plastic that would hold up at constant 362-degree temperature, but would also have abrasion resistance. Where would you look, amorphous or crystalline?
Okay. Would that participant write in and let us know if that's 362F or 362C?
All right, so we'll wait for that. And then there's another one. Is there a test method to test a specimen in tensile application that is notched, specifically asking if there can be a relation to notched materials and tensile?
You know, I'm only familiar with the standard ASTM test, I don't know if there is a standard test to test a notched tensile specimen. I would imagine that that could be easily done by a lab, and there are commercial laboratories who do that as contract work. And there may be an ASTM test with a notched tensile pull. And the website for ASTM is astm.org, and you can explore their tensile test to see if they've got one.
All right.
The standard, I'm sorry, Wendy, I didn't mean to cut you off. The standard tensile test is D638, and then you can look for other tests that are tensile and perhaps have a notch in the specimen.
All right, and we heard back about the 362 degree and abrasion resistance. It's Fahrenheit.
Okay. I'm going to try and keep this answer relatively short, but there's a little bit of complexity to that question. The first thing I'd have to look at is that 362F. And as you heat up a plastic material, it'll get softer and softer and softer the higher temperature you go. So if you look at a graph that graphs the modulus or stiffness of a material at elevated temperature, you'll see that they get softer and softer and softer. And the first consideration I have, and I believe Larry DeSanto gave a terrific presentation on dynamic modulus, I start to look at the temperature at which that plastic would lose stiffness rapidly. I would look for the knee to that curve, and I would try and find a plastic that didn't lose too much of its stiffness at 362F. That's number one. Number two, I would look at the thermal stability of that plastic at elevated temperatures. Now, to give you an example in your everyday life, think about the oldest pot in your kitchen that has that black phenolic handle, and it gets really chippy by the screw, and it starts to chip off, and that handle actually wobbles. There are graphs that will show when plastics will degrade at certain temperatures over long periods of time. And those time to 50% loss of tensile strength graphs will give you rich information about not what that plastic will do in 5 minutes, but what it'll do at 1,000 or 10,000 hours. And that would be a super important consideration. The third very important consideration are the creep characteristics of that plastic. When you think about creep, it's this slow movement under load. So if you go home and you roll your refrigerator out from its customary spot, you'll see dents in the linoleum on the floor. And that's that slow movement under load. And at elevated temperatures like 362F, you start to see significant creep characteristics. So there are several things that you have to consider when considering an abrasion-resistant application at 362F. To give some general comments on that, I would start to look at any number of materials as possible candidates. One good one is PAI, polyamide imide, which tends to have good high-temperature performance. Another good one is polyimide, PI. And finally, really shifting gears on you, there is a thermoset material called G7, which is a combination of silicone matrix and glass fibers that can start to play around at those types of elevated temperatures. I'm not saying one of those three is the right candidate, but they're decent places to start. So as I mentioned before, Wendy, and I appreciate that participant asking that question, because there is a tendency in our industry to just label everything with continuous service temperature and say, oh, well, it'll take 300 degrees. And that's the quick and dirty answer, but when you really dig into it, there's a little bit more complexity to it. Wendy, was that the longest answer for a difficult question you've ever had?
No, that was great. Thank you very much. We've got 2 more, and then if anybody else has any additional questions, please email them to me, and I will share them with Keith. But one of the last 2 was compare PVC and PPL for HDT. Won't PPL deflect at 264 psi and lower temperatures?
It is PPL or PPS?
PPL.
I'm not familiar with PPL.
All right. If the question asker could clarify, then that would be great. And then the next one would be, what is the difference between tensile strength and elongation?
Okay, that one I can answer. Let's say I take a piece of plastic and I pull it apart. I'm going to measure two things as I do that. One is, what load did it take for me to pull it apart? How hard did I have to pull it apart? And number two, if it started at 1 inch long, how long is it going to get before it snaps? So if it started at 1 inch and it finally snaps at 6 inches, I call that 600% elongation. It's how much it stretched before it broke. Or some people will measure how much it stretched before it permanently deforms, which is tensile elongation at yield rather than break.
All right, and the previous question asker, the PVC and PPL, he was referring to polypropylene.
Oh, okay, I apologize. So if we look at PVC and polypropylene, could you re-ask the question, Wendy?
Compare PVC and polypropylene for HDT. Won't polypropylene deflect at 264 psi and lower temperatures?
Well, I think it would depend on the type of polypro and the type of PVC. They both tend to be low temperature materials. Polypropylene is available in a couple of different chemistries. There are copolymer propylenes and homopolymer propylenes, and the copolymers will tend to have lower HDTs. PVC is available in rigid versions and plasticized versions, and the plasticized versions will tend to have lower HDTs. So I don't know the answer for that specific grade of prop and that specific grade of PVC. I think of both of them as materials that I try not to use above temperatures of, say, 160 F, because they're both low temperature plastics. I think the short answer would be, it would be very grade specific. I couldn't make a generalization about the HDT of PVC versus polypro.
All right. Well, thank you again, Keith, and thank you for taking time to answer the questions this morning. I'd just like to remind everybody that you can download the IAPD Thermoplastics Rectangle and view upcoming events and web seminars at iapd.org. Thank you very much for coming, and we look forward to seeing you again soon.
Thank you very much for having me.